Okay, so today we're going to move on to a lesson that involves using your Ka chart. So we've kind of referred to it just briefly. So today we're going to take a look at how it works and how it can help us predict the products in a reaction. So these reactions involve a competition between two bases for a proton. Okay, so when we're talking about the two bases, we're talking about the base that appears on the reactant side and the base that would appear on the product side. So one's the base and one's the conjugate base. So when you're looking at something like this, how do you decide which one's the acid and which one's the base? They both contain hydrogen ions, so they both could potentially deliver a proton or a hydrogen ion to the other. So what you can do is you can use your Ka chart. Okay, so in this particular case, I'm just going to show that this is hydrofluoric acid. So this would actually be the proton donor in this case, but we're going to look at it in a minute on the chart just to show how it works. So this would be our acid. Then this would be our base. And because this hydrogen is zipping over here, this would become acetic acid. And this would just become the fluoride ion because it lost its hydrogen. So remember, you can always pair together. If this is your acid on the reactant side, then it's going to pair with this guy here, and this is going to become the conjugate base, okay? And these two pair together because you're always pairing the ones that differ by only one hydrogen ion. So this would become your conjugate acid. So we want to use our Ka chart because it's not always super clear which one's the acid and the base. In this case, this one, you're probably familiar with hydrofluoric acid, so you would know, but you wouldn't always know. So these are the steps we use to use the Ka chart, and I'll kind of refer back to it as I go. So one of the reactants will act as an acid, the other as a base. So acid's the proton donor, right? Here it gave the proton, the hydrogen ion. The base is the proton acceptor. If the reactant is on the left side of the Ka chart, it is an acid. If it is on the right side, it is a base. So let's just take a look at that chart just so you know what I'm talking about. Okay, so these guys here in this column, these are acids. So if this is just showing the reaction with water, okay, and then on the other side, it's producing the base or the conjugate base, right? So the strongest acids are found at the top of this chart. So this would be, these are your strongest acids here, and they get weaker and weaker as you go down. And it works the opposite way with the bases. So this is your weakest base, and they get stronger and stronger as they go down. So these are the bases, these are the acids. Okay, we'll come back to this chart in a minute. Okay, so if both reactants, so if you're looking at your two reactants and you find that they're both in that left-hand column, they're both in the acid column on your Ka chart, how do you decide if they're both considered to be acids, which one is going to act as the acid, which one's going to donate the hydrogen ion or the proton? The one that is higher on the chart will act as the acid. So the stronger acid. Once you have determined the acid and base, the acid will donate a proton or a hydrogen ion, and the base will accept the proton. You're then going to label your conjugate acid and conjugate base, just as we've done in the past. Once you've got all 4 species labeled, you're going to compare the 2 bases. So that's going to be the base on the reactant side and the base on the product side. The one that is lower on the chart will be the strong base, while the other one is considered the weak base. Okay, so the strong acid and strong base will always be on the same side of the equation. And the reaction will proceed in the direction of the weaker acid-base pair, because the strong acid and base ionize or break up to a greater extent. Okay, so let's use our original example, and we'll use the chart this time to decide and show how this all works. Okay, so I have hydrochloric acid, and this is the acetate ion. So let's look at the chart. Okay, so we can find, let's see here. If you scan, here is, I'm just going to use like yellow or something. Here is the hydrofluoric acid, and the acetate ion is right here. Okay, so in this case, we can clearly see, well, this is the acid and this is the base. This one's found in the acid column, this one's found in the base column. Okay, and you can see that when hydrogen or hydrofluoric acid gives away hydrogen, it becomes just the fluoride ion. And if you look over here, if you go backwards, when the acetate ion gets a hydrogen, it becomes acetic acid. Okay, so that can help you finish off your equation. Okay, so we're going to write in okay, we said this was the acid, this was the base. Okay, now I'm not going to write Ca and B Cb, I'm just going to use the acid and base symbols again for my conjugate acid and conjugate base. Okay, because this time around I'm going to label them as strong and weak acids and bases. So this would be the conjugate acid because it pairs together with the base, and this would be the conjugate base because it pairs up with the acid. So now what I have to do is decide which pair are the strong acid and base and which pair are the weak acid and base. And they're always going to stay together on the same side of the equation. So I go back to my chart, okay, and I'm going to compare the 2 bases. So the acetate ion and the fluoride ion. So where do I find those? Well, here's the fluoride ion, and here's the acetate ion. So we know that base strength increases downward, so the acetate ion is the stronger base and the fluoride ion is the weaker base. So I'm going to go back and I'm going to label that the strong base is the acetate ion. Therefore, this would be your strong acid because they're always going to pair together on the same side. And these guys then would be the weak acid and the weak base. So this is a reversible reaction, meaning it can happen, right? It can happen in the forward and reverse directions. The forward direction is favored, okay, because strong acids and bases will ionize more, meaning they'll break up into their individual ions more so than a weak acid and a weak base. So in the reverse reaction, you're only getting a small amount of that happening, like a very small fraction, whereas with a strong acid and a strong base, they're almost completely separating or ionizing. So we would say that the forward direction is favored from strong to weak. So let's try some more examples just to get some practice here. So here we've got, again, in this particular case, you would probably easily be able to tell that this is your acid and this is your base, because this guy here doesn't even have a hydrogen ion to donate. However, we can look at our chart to be sure. Okay, so we're looking at H2CO3, which is here, and the, what was it, SO3, 2 negative ion. And that's right here. Okay, so you can see it's on the acid side, that one's on the base side. Whoops. So the hydrogen ion, you don't have to draw that in. That's just what I do to show what's happening, but it's not required. So there's my acid, there's my base. So if the SO3 2 negatives receiving a hydrogen, now, does it have a charge? Well, you can always go look at your chart. So let's go look. Here's the SO3 2 negative. If you go back, here it is with a hydrogen attached. So it's HSO3 negative. And you get, instead of H2CO3, you're getting HCO3. And again, does that have a charge? Well, let's take a look. If you look over here, this shows that once it's lost a hydrogen, it's HCO3 negative. Okay, so let's do our conjugate acid and conjugate base. So this would be the conjugate base, and this one would be the conjugate acid. I'm not actually doing the Ca and Cb because I'm going to label these in terms of strong and weak. So to figure that out, I look at my two bases, HCO3 negative and SO3 2 negative, and I find them on the chart. So here's the HCO3. And the SO3 is here. So because it's lower on the chart, it's the stronger base. So it's going to get labeled strong base. Therefore, this is the strong acid, and that makes these two weak. So it's always going to favor the direction from strong to weak, because these guys are going to ionize more. So I would say the forward reaction is favored. Okay, looking here, again, we would clearly know this is the acid because it's the only one with hydrogen. This guy doesn't have any hydrogen, so this is going to be our acid and our base. And then we're going to show that we get a hydrogen with NO2. Okay, so let's just look at our chart to make sure we get our products correct. So H3PO4, when it loses a hydrogen, becomes H2PO4 negative. And NO2, when it gains a hydrogen, is HNO2. Okay, now this would be our conjugate acid, and this one would be our conjugate base. So let's compare our two bases, H2PO4 and NO2, and see which one's stronger. Here's NO2, and here's H2PO4. So NO2 is further down, so it's the stronger base. So that means that's the strong acid, weak, weak. And again, it's going to be the forward reaction favored. Okay, so looking here, you would probably guess this to be your acid, but considering they both have hydrogen in them, let's just double check. So we have HPO4, which is here on the acid side, and NH3 is over here on the base side. Okay, let's just, while we're here looking, when HPO4 loses a hydrogen, it becomes just the phosphate ion, PO4 3 negative. And when NH3 gains a hydrogen, it's NH4 plus, the ammonium ion. All right, so acid, base, we get NH4 plus, and we get PO4 3 negative. So this would become our conjugate acid, this one our conjugate base. And now let's just check our bases. So we've got the phosphate ion to check and ammonia. Oops. Okay, so here's ammonia and here's the phosphate ion. So the phosphate ion is the stronger base. So that means these two become the strong and these two become the weak. So this time it's the reverse reaction that's favored. Okay, I'm just going to add in one more example up here to show you one where you've got two acids as reactants, or two that appear in the acid column, and how to deal with them. Okay, so H2CO3 and H2PO4 negative. So which one of those two is going to act as the acid? So let's find them on our chart. H2CO3 is here and H2PO4 is here. So remember, stronger acids appear higher on the chart, and it's the stronger of the two that's going to act as the acid. So in this case, it's the H2CO3 that's going to donate the hydrogen. So this guy will be our acid, and that one the base. So the hydrogen is going to zip over. So we're going to end up getting HCO3. And if we look, HCO3 has a negative charge, and H2PO4 will have to become H3PO4 because it's gaining, and it's got no charge, it's gaining a hydrogen. So HCO3 and H3PO4. Okay, so this would be our conjugate acid, conjugate base. So let's compare our bases, HCO3 and H2PO4. Okay, so here's this guy here and the H2PO4. Where are you? There you are, up here. Okay, so this is lower down, so that's going to be our strong base. Making this our strong acid. Weak, weak. So this one would be the reverse, favored. Alrighty. Okay, so now let's just talk a little bit about strong and weak acids and what Ka is. So we've already talked about KEQ, KSP, KW. We have a variety of these K constants. and they're all specific to a certain thing, right? But they all have to do with an equilibrium constant. So there's also an equilibrium constant for acids, and we call that Ka. So let's just talk about the difference between a strong and a weak acid and how this concept of Ka applies. Okay, so we've talked about this already, but strong acids dissociate or ionize almost completely, 100% in water, right? So they completely break apart. For instance, hydrochloric acid is a strong acid. So in water, it basically completely separates out. It does form, so like this hydrogen jumps on with water to make the hydronium ion and the chloride ion. But to simplify, we always just replace this hydronium ion with H+, just for simplicity. So when it's a strong acid, a single arrow is used because the reaction runs almost entirely in the forward direction. Strong acids make strong electrolytes because they dissociate so much. So there's lots of ions in solution. So they are excellent conductors of electricity. And if you were to solve KEQ for this type of reaction, it would be extremely large because almost all of the acid dissociates. So this is what your KEQ would look like. You've got your products over your just this reactant because water's in the liquid state, and you'd get a really, really large value for KEQ. So a strong acid, though, can still be dilute if it has a low concentration. So don't mix up the concept of a strong acid with the concept of concentrated. They're different things, right? So you can have a strong acid that's very dilute, right? If you just add a small amount of it to water. And you can also have a strong acid that's very concentrated. So for example, 12 mole per liter hydrochloric acid is a concentrated strong acid. In fact, it's so strong that the pH is actually off the scale. It's -1. So strong acids contain these ions, halogen ions like chloride, bromide, iodide, and also these ions, nitrate, chlorate, and sulfate. Oops, too negative. Okay. Weak acids, on the other hand, only dissociate or ionize a little. So not much product is found at equilibrium. They are very weak electrolytes because there's so few ions in solution, so they do not conduct electricity as well as strong acids or bases. So an example, dissociation of acetic acid. So here's acetic acid. Notice now we've got the double arrow because it's not as strong of an acid. So there's going to be both directions occurring here. These are what it dissociates into, the hydronium ion and the acetate ion. And if you set up the KEQ, you would set it up like this, right? You just wouldn't include water because it's a liquid. So because the concentration of the products is so low at equilibrium, for your weaker acids, your KEQ is much, much less than 1. Okay, so let's make a specific K constant for acids, and we're going to call that Ka. and Ka stands for acid dissociation constant. So you set it up in the same way you'd set up any KEQ formula, concentration of products over concentration of reactants, but we're going to replace the hydronium ion with just the hydrogen ion. Okay, so a strong acid would have a high Ka and a low pH, and it dissociates a lot. A weak acid has a low Ka value, dissociates only a little, and its pH would be higher. So on your Ka chart, stronger acids are on the top left and weaker acids on the bottom left. So it just goes from strong down to weak. So let's just practice writing some Ka expressions for acids. So we're going to write the dissociation equation, then we're going to write the Ka expression using H plus instead of H3O plus. And then we're going to see how we can just pull the value of Ka off our chart. Okay, so we're going to see that HCl breaks apart into H plus and Cl minus. Let's just add in here that these are all aqueous. Okay, so when I write Ka, what I would do is I would write Ka equals H plus concentration times the Cl minus concentration over the concentration of HCl. So you can actually use your chart to find the value of Ka for hydrochloric acid. So let's just look here. So here's hydrochloric acid. If you go across, these are the Ka values. So notice for the strong acids in the top left hand corner, all you get is, it just says very large. So it doesn't even give you a value. So all we would write down for hydrochloric acid is that the Ka equals very large number. Okay, let's try this one. So HSO3 negative. Okay, now I'm going to show the double arrow here just because HCl, anytime it's a strong acid, so hydrochloric acid's a strong acid, you can use a single arrow. Anything on your Ka chart that doesn't say very large next to it, you would use the double arrow. So this would break up into H plus and SO3 minus. Okay, so Ka, would look like this. And let's see what it's equal to. So we find HSO3. Here it is. So we're just going to go across, and we can see the Ka value is 6.2 times 10 to the negative 8. There we go. So let's just look at this next section before we end. Okay, so a polyprotic acid basically is an acid that contains more than one hydrogen ion. Okay, so that would be something like H2 or H3 combined with an ion. So they have more than one proton or hydrogen ion to donate. So these acids will actually react in a series of steps until they have donated excuse me, all of their protons or all of their hydrogen ions. So for this one, for example, H2SO3, it has a total of 2 hydrogen ions to donate. So this will happen in 2 steps. So this is sulfurous acid. Okay, so let's look at the 2 steps. So first of all, we start with H2SO3. This is not a strong acid, so we're just going to use the double arrow. So it's going to break up into one, always just do 1 hydrogen ion at a time. So 1 hydrogen ion, and then that leaves HSO3, and if you check your chart, that's got -1 charge. Okay, so you would write the Ka expression as HSO3 negative times H plus divided by H, the concentration of H2SO3. And if we look at our chart, let's find that Ka value. So we find H2SO3, and we go across, and it's 1.7 times 10 to the -2. So we're just going to write that value in here. Now, I'm just going to go on to the next page to do step 2. Step 2 is now taking the product from step 1, which was the HSO3 negative. There's still a hydrogen there to donate. So let's do that in step 2. So it's going to donate that 1 hydrogen, and that leaves the SO3 2 negative ion. And you can always look to your chart if you're not sure about charges for these, and you'll find them. So let's just go back and label this Ka1, and here we're going to label this Ka2. So this is the second step. And you basically just continue to do the steps until there's no more hydrogen to donate. Okay, and if we go to our chart, let's find that value. So we're looking for HSO3 negative this time. Here it is. And if we go across, its value is 6.2 times 10 to the -8. Okay, so let's do one more just so you can see. So here's another polyprotic acid because there's 2 hydrogen ions. So we just show it in steps. Step 1 would be the H2CO3. It's just going to get rid of 1 hydrogen at a time. That would leave HCO3. And if you check your chart, that's got a negative charge. So Ka1, you'd write out the expression. And we look up the value for that. So we're looking for H2CO3. Where is it? Here it is. 4.4 times 10 to the -7. So we would put 4.4 times 10 to the -7. Now for step 2, we're going to start with this and break it apart. So it's going to lose that hydrogen, and then it's the carbonate ion, which has a -2 charge. Again, you can always refer back to your Ka chart to figure out these products. So your Ka2 expression looks like this. And let's look up the value. We're looking for HCO3 this time. Where is it? Here it is. And it's 4.7 times 10 to the negative 11. Okay, so you can work on worksheet 7 and 8. The worksheet 7 involves figuring out which ones are the strong and weak acids and which direction the reaction will proceed. And worksheet 8 is doing this kind of thing. So give those a try for practice.